concept to help support sustainable agriculture. So it's a novel concept, and it's actually the subject of my current PhD study. And my PhD study is being supervised by Professor Phil Jordan at Ulster University, Professor Rachel Creamer at Wageningen University in the Netherlands, and also Professor Roger Schulte from Chagast. So this is very much a snapshot, an introduction to the concept of functional land management. So firstly, if we just look at the situation in terms of food production and global food security, as you all know, the global population is expanding. By 2050, it will have reached about 9 billion. So there's an increased demand for increased food production. That means that we will have to intensify agriculture to produce that additional food. However, we cannot intensify agriculture at the expense of the soil resource or the environment. So we can't, by intensifying agriculture, lead to, for example, soil degradation, such as soil erosion, soil compaction, or nutrient depletion, or indeed an impact on water quality, such as eutrophication, or the sort of release of carbon dioxide from our soils, which can actually contribute to climate change. So this new concept called functional land management, which was introduced by Professor Roger Schulte back in 2014 in a paper, helps support sustainable intensification. What sustainable intensification is about is that we can increase the production of food from our land, but we actually do that in an environmentally sensitive manner. And this new concept helps support sustainable agriculture. So what is the actual concept of functional land management? Well, it's very much focused on the provision of soil ecosystem services, or as we refer to them as soil functions. So it's really about harnessing those soil functions to help achieve sustainable intensification. So in order to meet the targets in agronomic policy, so for example, Food Harvest 2020 strategy in Ireland, or Foodwise 2025, we need to produce more food in a sustainable way, and also to meet those agronomic targets, but also meet our obligations in terms of the agri-environmental legislation, such as the Nitrates Directive, the Habitats Directive. This concept helps support that, and it's very much focused on maximising the supply of soil functions to achieve sustainable agriculture. I should mention that there is the potential for the concept of functional land management to be applied across a range of scales, from farm level right the way up to continental level, and this is the actual subject of the Chagast Landmark project, which is currently underway. However, for today I'm really focusing on farm level, just to introduce the concept. Now, the functional land management can actually aid decision making at farm level. In terms of land use planning, in terms of where we can actually increase the production of biomass, food, fibre, fuel on the farm, but how we can actually do that in an environmentally sensitive manner. And what's central to functional land management is the soil resource, is the actual selection of the soil type on the farm, which is best at supplying the preferred suite of functions for a particular land use. And the one thing that we need to be mindful of, though, is the supply of those soil functions will vary dependent on the soil type, the land use type, and the land management type. So if we look at the soil ecosystem services, which I refer to also as the natural capital of the soil, and we have 5 key soil functions in agriculture. I suppose the most obvious one is biomass production, where we actually can produce food, fibre and fuel. We need to supply, in order to supply the global population with food, we're going to have to increase that function. We're going to have to maximise that function to produce more food, fibre and fuel. But we cannot do that at the expense of the other 4 key soil functions in agriculture, which are carbon sequestration to help combat climate change, water purification, for example by denitrification or phosphorus sorption, nutrient cycling, so for example we can use the soil to actually recycle organic manures, and also habitat for biodiversity. The soil is very rich in terms of, a healthy soil is very rich in terms of biodiversity. So in terms of functional land management, we want to actually make sure that the soil is able to deliver each of these soil functions and to the highest possible capacity that it can. One of the key outputs from the first stage of my PhD is this soil functions matrix, and I have a paper published on this. Now what this actually looks at is the multifunctional capacity of the soil and how that varies dependent on the soil drainage type and the land use type. So along this side of the actual matrix, it shows you the soil drainage status, which ranges from well and excessively drained to moderately and imperfectly drained, poorly drained, and then peat soils. On top of the matrix here, we actually have the land use type, which includes arable, bioenergy, broadleaf forest, coniferous forest, managed grasslands, other grassland, and naturia. Each box within the matrix actually represents a soil function. So the actual box itself represents the multifunctionality of the soil. The purple represents the capacity for nutrient cycling, the green habitat biodiversity, the grey carbon sequestration, the blue water purification either by the process of denitrification or phosphorus sorption, and then finally primary production. Now this is very much a qualitative representation where the size of the box is used to indicate the actual change in capacity of the soil to deliver that particular function. In order to explain it a little bit more easily, because this is quite complex, I'm actually just going to extract part of that matrix and just zone in on it a little bit. So if we look at arable land, for example, we'll just focus on arable land. You can actually see how the capacity of the soil to deliver each of those 5 key soil functions varies, okay, depending on the soil drainage status. So under moderately and imperfectly drained soil, we can see that this is a very good soil type for the production of biomass. So for production of crops, moderately drained soils are very, very good. They're also very good at recycling nutrients because firstly there is a demand for nutrients in arable farming because the plants are uptaking nutrients and there's a constant need for replenishment of nutrients. So therefore they tend to be very good at recycling nutrients such as in organic manures, for example. However, these moderately drained soils are not very good at water purification, for example by the process of denitrification. They're also not very efficient at carbon sequestration because they're actually very well aerated, and that actually facilitates the microbial breakdown of the actual organic matter in the soil, which actually ends up then releasing the carbon dioxide to the atmosphere. So although these moderately drained soils are very effective at the functions for food production, the growth of crops, for example, and nutrient recycling, they are not very effective and have a lower capacity for the delivery of the function for water purification and for carbon sequestration. However, if we actually look at the poorly drained soils, which would be typically known as lower productive soils, these soils, as you can see, the white box for biomass production is smaller, so they have a lower yield of crops. They're less effective at nutrient recycling. However, the poorly drained soils are actually very effective at carbon sequestration because there's very poor aeration, and that actually reduces the microbial breakdown of the organic carbon or the organic matter within the soil. They're also very effective at water purification by the process of denitrification, which actually requires saturated conditions to convert surplus nitrate into dinitrogen, which is released into the atmosphere. So in terms of decisions at farm level, if a farmer, for example, is part of an agri-environmental scheme and wants to use part of a farm to increase carbon sequestration, the best area would be where there's poorly drained soils. That's the best at carbon sequestration, and that can actually be enhanced further by choosing the correct or appropriate land use type. So on poorly drained soils, carbon sequestration can be increased further by the plantation of forests or by the retention of forest ecosystems. That's the most effective. In terms of carbon sequestration, the worst possible scenario is where you have very well drained soils that are under arable land. That is the worst case scenario. Just to conclude, so all soils contribute to sustainable agriculture by means of supplying soil functions. The supply of those functions will vary dependent on the soil type, the land use type and land management. And functional land management provides a tool to aid decision making at farm level. I have a number of publications on my work, so to date, and if anybody wants some more information, please do let me know. And finally, just to introduce a new course that we have, we just launched it this year at IT Sligo, which is a BSc in Agri-Food Science. As I said, it's a brand new course, and we look forward to establishing relationships with people in the agri-food sector over the coming years. Thank you very much.